All right. Good morning, everybody.
Okay, let me introduce you.
Oh, okay.
So our next speaker is Nikolai Hayden, and he will talk about a return time distribution for dynamical systems. So Nikolai?
Yeah. Okay. Good morning, everybody. Yeah, I forgot the title because that's the first time ever I used Beamer. So I want to talk about return times. So a typical setting will be um, normally a measure space, but today I'm going to use a metric space because I'm going to talk about metric setting. We have a map and an invariant probability measure. Then what you want to do, you're going to cut out an area, say U positive measure, and count the number of hits up to a certain number, up to a certain time. So this capital N is the orbit, length of orbit we're actually going to look at. And I will say something more. I will have to say something more about it because it matters a lot. How we're going to choose this. Now, this Z sub U super N tells you how many times you're going to hit to this U. So the classical setting, which I didn't write it, some other place I wrote it, there's the so-called return time or entry time, which measures the first time you're going to hit, which means for every capital N below that, it's going to be 0. And for this, there is this old formula from Katz from 1947, which tells you how this on average scales, which is the reciprocal of this, of the measure of u. Oh, there's a typo here. It's mu of u has to be positive, not mu of omega. The classical setting then is, and I look at return time distribution, is to take this u to be little neighborhoods of a point, then to shrink it and to scale the capital N appropriately, so that you get some meaningful distribution result. So what we want to look at is a somewhat more general setting. We want to get, instead of a point, we want to use some set gamma, some null set gamma, and then fatten it up, and then look at how long it takes to distribution of return times, and then to shrink it till one gets down to this gamma. So that's why this formula there. There's mu of z sub b rho, n of rho, depending on rho, and takes rho neighborhoods. And t's are just some parameter. It doesn't play too much of a role. But the point, of course, is a capital N sub rho. How does one have to scale that in order to get some non-trivial distribution? So for every t, one takes rho to 0 and gets this distribution here. So the point here is that one has to make this work in some meaningful way, one has to have some mixing properties. Because if one doesn't have mixing properties like just ergodicity, there are these examples by Lacroix. One can construct neighborhoods that shrink to a point, say, and can produce any limiting distribution on one. So the limiting distribution kind of relates to some mixing properties. So the ones typically being done are to take care of correlations, which I will say more about today, or one can do mixing properties, like the one here, for instance, phi mixing. Oh, this is right phi mixing, because on the right-hand side, in the R estimate, there's a mu of C, but could just as well have a mu of B, and one gets then sort of a mirror image of results that are really more or less the same. The point here is that J is the gap, because B sort of is composed of, like it's a symbolic setting of n words. C is arbitrary, but to the right. And then when one pulls back the C by n plus j many times, one creates a gap of j that makes the mixing property then. So here, this is what people have been doing for quite some time. Essentially in modern times, beginning with Pitzcliffe in 1990, a single point. He studied it for axiom A systems, primarily on symbolic systems. So if one had, in more general terms, a lot of people have contributed towards that phi mixing with respect to a partition, one gets generically Poisson distribution. provided X is not periodic. There's this dichotomy which happens that the limiting distribution for non-periodic points is one thing, usually very regular, and for periodic points one gets something, well, yeah, I'll come to that in a second. One gets something else, but the point here is the scaling. One has to apply this capital N, Z super capital N, this here, this scaling here, is the one essentially suggested by Katz's theorem for manifold 47, which is, there's a parameter T in there, which is arbitrary. But the 1 over mu of AN is exactly the average value for the entry time. That's what I call it, the Katz scaling. If one has a periodic point, minimal period P, then one gets that this very same quantity goes towards Polya-Apley, which is compound Poisson distribution. There are two parameters there, namely there's the Poisson parameter T, and then there's also geometric parameter theta, because sort of if one thinks P is equal to 1 and has a fixed point, then sort of every time locally it gets stretched. And so one loses a percentage of the neighborhood. And this is where the geometric part comes in. So what's left over is kind of like 1 minus theta is what's left over. Theta is the amount that stays, 1 minus theta is the escape part. And the cut scaling then has to already be adjusted by some term here, 1 minus theta. With theta equal to 0, of course, essentially corresponding to the non-periodic type. Well, one can write down for Polya-Apley what these distributions are in explicit form. So that's what it turns out to be. It turns out to be this formula. For theta equal to 0, there's only one surviving term in this sum here, which it gives you Poisson, of course. Pitskill back then, computer for axiom A system 1990, and got a value for theta, which I call the Pitskill value. If you have a potential, then you get this number here. And this works quite well, say for one-dimensional maps. One can get this also for one-dimensional maps. So this capital P is the pressure, this kind of an average value. One has to take it out. So this pressure of what's up there should be 0. So this is a normalizing term. And one gets essentially these kind of like expansion rates along the orbit. That's what one picks up. So here, to remind ourselves what a compound Poisson distribution is, because I've talked a little bit more about this. So capital P is just straight Poisson. And then one adds up these IID random variables that assume positive integer values, namely hits. They're counting hits. And one counts here up to this Poisson distribution. Essentially what this Y does is the hits don't come in an isolated way, they come in clusters. And the capital Y sub j, the value of the capital Y sub j is essentially the size of the jth cluster. And the Poisson tells you these are the actual clusters that come. And in that way, kind of it makes more sense when one looks at the non-periodic setting we had sometime, if I may scroll up. This one here, in the non-periodic point, there are no repeats. So once you leave for return a long time, Katz time. So the classes are all of size 1. You don't see anything compounded here. You just see the straight Poisson. You just see this part here, the P part, if this capital Y. So this comes in if you have periodic type of behavior. If it's just a single point, a periodic point, and if it's a gamma more generally, then you come back sometimes. It becomes far less predictable. And here the special case is the simplest non-trivial compound Poisson is the Polya-Apley, and this is geometric. These parameters lambda tell you essentially cluster size, the Y sub j. In the straight Poisson, it's just 1, and Polya-Apley, they are geometrically distributed. So if one wants to look at it more generality, then one has this set gamma. Instead of a point, one has a gamma, which is a null set. And one wants to take a limit down to that. So one takes neighborhoods, and they have positive measure. And wants to restrict further and further down and see what happens in the limit. Then these are the parameters one has to look at. The bottom one means a normalizing term is you're getting at least one hit, which means there should be at least one cluster. At the top, it means you have L hits. And now the capital L, the observation time should be relatively short with respect to the capital N in the end, so that the probability that you're going to hit something is most likely a cluster. So you're seeing a cluster here, and that's why the double limit. We take rho to 0, which means this capital L is next to nothing. So if you're going to hit something, it must be a cluster of length L. And then you let capital L go to infinity because clusters could be absolutely long. So these are the parameters we have to get out of the distribution. Now there's an interesting thing which means it can be related to conditional returns. So if one conditions on a neighborhood and looks at L, then chances are this L, this small L, many must be a cluster that starts at position 0, but it could have been going on before that. We do not know. So there's some, then one takes the usual thing, double limit, rho to 0, L, capital L to infinity. One gets these numbers, alpha L. These are called the extremal indices. And there's a nice relationship, a very simple relationship between just plain entering and actually returning, because this one on the right-hand side is conditioned on actually starting out in the neighborhood and then see how long are we going to stick around. Then one gets this relationship here. And in particular, one interesting aspect of that is if we take limits, it's going to go to this constant alpha 1, which people sometimes call the extremal index. And what it says is you enter here and you take the proportion what you would expect with a capital L hits up to the time. It's kind of a defect. You're measuring a defect here. And this is becomes a normalizing term. Well, you can prove it very easily simply through such an argument. I'm not sure I want to do it now. By simply cutting it up and using invariance, and then you come out with this. And of course, it's irrelevant what this gamma sub rho is. You can play this with any set. Yeah, this capital L mu of gamma L is essentially the Katz scaling term. Here's the theorem. This is theorem, Katz's famous theorem, that no matter, gamma rho is irrelevant. You put in the same thing as you put here. Then you get always 1, which tells you the average length is simply 1 over the measure of it. Now, between this alphas, the extremal indices, and the cluster probabilities, there's this relationship, which is this one here. Namely, the clusters are essentially deduced from the differences, but you have to include a normalizing factor. The normalizing factor is because what people call the measures are size biased. Because they show up more often with respect to the size, because if you begin in a cluster, you don't know where in the cluster you actually begin, because you only see the future of the cluster. You might have been there before. So which means you see, once you enter a cluster, you see it more likely, and this one is supposed to normalize for it. So what I want to talk about, some general result for which in a geometric setting, not the symbolic setting with phi mixing, but in the general setting, when we have a manifold, and generally what we want is we have some expanding map. One could think of, say, interval maps. One could think, yeah, interval or torus maps. One could think of that. Then one gets some inverse branches, I and other inverse branches, because we need them. Then you want to make sure that these inverse branches don't behave in some weird way, which means they're kind of getting too small. So each of the inverse branches somehow are defined on a sizable set. These are these balls. So we want to be able to cover the whole set by some uniform balls. And the reason for that is so that these measures are uniformly bounded from below. Again, interval maps have it immediately satisfied. Markov measures, and anything Markov immediately satisfies this condition. And here's some lingo, an N cylinder, and that setting is simply a pullback of one of these balls on which an inverse branch is well defined. Now, in reality, this can be improved on because we can allow for some bad sets like parabolic points and whatnot, and has to put in some controls, but never mind, not for today. So these are geometric conditions we have to have. Then we have some dynamic conditions. So we want to have some mixing condition, decay of correlation in that case. Well, the C of k has to decay in some polynomial way, good enough, depending on some other parameters, depending on how bad other stuff can be. Distortion on these cylinders, distortion should be not too bad. Classically, you would assume boundedness, but it doesn't have to be. You can cut it a little bit of slack at the expense of, say, decay. There has to be some contraction. Well, sure enough, typically we expect the exponential. The measure has to have some dimension with respect to this neighborhood. That makes perfect sense. And then the always present annulus condition, because the gamma rho will be approximated by this cylinders zeta. So these are the dynamic conditions. You need the calculations, distortion, contraction, dimension, and the always present annulus condition. Then we can make the following statement. Namely, if you scale in a good way, then the distribution will converge to a compound Poisson distribution. This is compound Poisson, which is determined by the parameter t, which you just stick in, and the lambda L, which compute these are the probabilities for the clusters. So nu is the compound Poisson distribution on the integers, on the non-negative integers. And the main part here is this, the observation time scales in that way. So what you see here is actually this capital L is this one divided by L. So it is a percentage per symbol or per iterate, you can say, to actually hit this, which is not always the measure of the neighborhood, but typically will be less than that. And this is the right quantity to use, which is not always the cut scaling, because when we go back to the parameters, to the extremal values, if you allow me to scroll up, this alpha 1 can be 0. And in that case, this formula can't be used to compute the lambdas from the alphas. This only works if one has a cut type scaling where the alpha 1 is actually strictly positive. But you get a result like this no matter what, whether alpha 1 is 0 or not. This scaling always works. This comes, of course, if you have cut scaling, then essentially you have this adjusting factor down here, which comes from the lemma we earlier had with this one slide proof. Well, this behaves roughly like that. Normally, you would assume there should not be any alpha 1, but this normally only if it's, say, a non-periodic point and gamma is just a non-periodic point, then you get this being to 1. Otherwise, you don't. And of course, only in that case, if it's positive, then you can determine the lambdas from the alphas. Well, some examples. Well, not much of a proof today. For instance, G2 maps, interval maps, single point, classical setting. Then geometrically, you can convince yourself fairly easily. You get a Pittsfield value here for the for the measure of max for the absolute continuous invariant probability measure. And this one is, and you get the alpha L lambda L is polyaptly. This is a Pitchell value here because you can write the exponential of the potential function, which is the logarithm of the derivative. Suppose you take many points. Same thing, C2 map an interval, many points. Then this converges to Poisson. You still get cut scaling though, but the lambda parameters now are different, or linear kind of combinations of these. These are the Pitchell values for each individual one. But the combined lambda L now is this one here, the HR, the density of the absolute continuous invariant measure. Suppose you take a product of two nice maps, and one has a periodic point. So, this is a 1, supposed to be a 1. T1 times T2, there's a typo. Each one has a measure. Take a product measure. So there's no coupling going on, nothing. Then you can also play around. Again, T hat is just the second return time for the second map under the power, and P is the period of that first point. So your set gamma down here is simply just this periodic point times an interval. Then you can write down these values. And then you get the convergence, and what are the lambdas? All the lambdas you can write, compute to that. You can compute alpha similarly. And theta, the value theta entering here is simply the Pitchell value for this. You can also take a more tricky map, Manville-Pomor, which has a periodic. This one has, if x is equal to 0, you see it's just slope 1, right? It's slope 0 becomes 0 here. You have an indifferent fixed point, and there's a problem there. If you just pick a point, just the origin, any other point is okay. At the origin, you get alpha equals to 1, alpha 1 equal to 1, and you don't get cut scaling. You get to Poisson if you do the scaling properly, namely, you do like in the theorem, namely here, you take this Z super L per L. This gives you a completely different scaling. You can compare this because you can, if you compute, you get kind of this asymptotics. But if you tried cuts, you would get a different asymptotics. You get this asymptotics down here. So you can see the difference there. Something goes wrong with the scaling. But since I perceive that I'm at the end of my time, then I won't say anything about the proof. The proof roughly splits into two parts. Well, three parts. You approximate by compound binomial. It's kind of a more straightforward part. And then you have to estimate using the mixing properties. And there's always a distinction made between long returns. That's where you use the correlation to curve correlation and the analysis condition. And then you have short returns. That's where you have to use this uniformity condition for the measures. But unlike in classical setting, you don't have to bother with a very short return because usually they had to be like, if you look at papers from Kolesha, so they have to spend a lot of time excluding very short returns, and that makes you exclude a set which is problematic, and that problematic set includes periodic points. But now, of course, we delight in looking at the periodic points because we're interested in the asymptotics we get there. But anyhow, I leave it at that. Well, thanks very much.
Thank you, Nikolai. So let's hold on a minute.